Okay, I accidentally just hit something and made it stop recording, so I didn't mean to do that. All right, sorry. Sorry for the confusion. Hopefully, I didn't screw anything up there, but I just turned the recording back on. What I was saying was we're going to start off with friction, and in order for me to explain friction to you, I want you to have a specific example in mind. I am fortunate enough to have a calculator that still has these little rubber buttons on there. Those are like little feet. And the fact that they're rubber makes all the difference in the world because this is a smooth plastic calculator, but when it's got those rubber feet on it, those little rubber feet actually give me a little bit of a purchase on the surface. In other words, they have better friction between the surface of the desk and the little feet. What I would like you to do is take something like this, something that isn't that easy to slide on your desk, and lay it like on your desk. Assume my hand's my desk. And what you'll find out is that when you push a little bit on it, if you push very lightly, it will not budge. If you push a little heavier but still not very hard, it still won't budge. And you can keep doing that until eventually you'll see what happens is it does budge, but then something weird happens. When it does budge, all of a sudden you'll feel a decrease in the force necessary to keep it moving, and you can push it forward uh, with that new force that's smaller than the force that you got it started with. So that's a phenomenon that we've noticed. And in fact, I've only seen static friction be equal to kinetic friction. Static is when the two surfaces are not moving with respect to each other. So you've got one object that ideally you want to move and another object that's the surface it's sitting on. If those two surfaces are in contact with each other and not moving, that's called a static situation. And the friction that's holding it still, keeping them from moving with respect to each other, is called static friction. Now, if on the other hand you have this object just moving across the table like that, that's called kinetic friction. And most of the time, the static friction is larger than the kinetic friction, but there are occasional instances where I found the static friction was the same. The reason why that's important is from a physics standpoint, it's important to know that kinetic friction is almost always weaker than static friction. And that, oddly enough, is the reason that your weatherman will try to teach you guys every time we have snowfall or any kind of ice on the roads, they'll remind you to turn into the curve. I'm going to discuss that a little bit so y'all have a better, hopefully, a better understanding of what turning into the curve means and why we say that. But the main thing is, I have to get you to understand our equations for friction. Okay. So, in order to do that, I've already explained how when you first apply a force, it's not big enough. So, the object that's sitting still on the surface does not move. If you push a little harder, it still doesn't move. You push a little harder, it still doesn't move. If you get up to a critical value, and I'm going to give you the formula for that critical value, then all of a sudden it will move. But once it starts moving, it's like a decrease in the force that's necessary, and you can push it along with even less force. So we need something to indicate that, and that's what I'm going to start off by showing you with a graph. So let me go ahead and share my iPad screen with you folks. Let's hope everything works. If mine jumps, if my iPad jumps Wi-Fi again, then I'll have to redo it. And it looks like it has. Why does my stupid thing do that? Let's see. Nope, didn't want that. Nope, didn't want that. Wi-Fi. It's on the right Wi-Fi, so that should work. Still not showing. Okay, hold on a second. I'm going to stop share and try it again. It's not supposed to be this difficult. Why are you being a pain? Urgh. Okay, let's check the Wi-Fi I'm on here. Ah, that's the problem. My computer switched to the different Wi-Fi. Now it should be good. Now let's do share, iPad, iPhone, share. There we go. So again, we're on chapter 5, And what I want to do to demonstrate exactly how the friction force works is I'm going to make a graph, and this graph is FA, the applied force. And I use the script F for friction. Your book does a capital F and then it has a subscript FR. I don't do that. I just use the script F that you might know from functions in algebra or whatever. So that's what I use. And sometimes some books will use capital N for the normal force. I use F sub N, and it looks like your book's mostly using that as well. But the main thing we're wanting to say about this is if you imagine, for instance, you applied a force of, let's say, 10 newtons, and we're going to say this is measured in newtons and this is also measured in newtons, then what you'll discover is, in fact, this would also be 10 newtons. So if we apply a 10 newton force, I'm going on the assumption that the 10 newtons is not sufficient to make it move. So it's smaller than the static friction force, and there's a maximum static friction force. Similarly, if you had a force of 5 newtons, then you would apply 5 newtons and you would get a friction force of 5 newtons. The friction force can't make the thing just jump and move, but what it's going to do is whatever force you apply, it's going to reach that up to some maximum, at which case it fails. So I'm drawing the equation for this as if it's y equals x, because that's basically what it is. So that's what I'm showing right there. But it turns out something critical happens once you get to a very specific value, and that specific value is mu static times the normal force. That is the maximum force that the static friction can muster. So if you push with a force less than mu static times the normal force, and I'll tell you what those mu statics are, there's a table for them in your book. But if you push with a force less than that, then the object doesn't move, period. No ifs, ands, or buts about it. If you push with that force, then the object is just free to move. And if you continue pushing it, it will break loose of that friction force. And then all of a sudden, what you'll see is that force will now drop down to some other quantity, and that new quantity is mu kinetic times the normal force. So that's the actual way that the applied force acts with regards to the friction force. Now, the equations associated with that are static friction is less than or equal to mu static times the normal force. Now, that's why we repeatedly, in problems that didn't need it, in other words, one-dimensional problems we were doing in chapter 4, we still, in some cases, took the time to compute what the normal force was, because we knew that the normal force was going to be relevant to friction, which comes in chapter 5. Now, the kinetic friction, F sub k, is just equal to mu sub k times the normal force. So those are the friction forces we'll be dealing with. And if you look, there's a table on page, I believe it's 117, at the bottom of page 117. It has the coefficients of friction. For instance, wood on wood has a kinetic friction equal to 0.2 and a static friction of 0.4. That's the mu s and the mu k, or actually that's the mu k and the mu s respectively. Ice on ice has a mu k of 0.03, whereas ice on ice has a mu static that's less than zero point 0.1 but pretty close to zero point 0.1. Similarly, metal lubricated on metal is 0.07 for kinetic and zero point 0.1 for static. Steel on steel unlubricated is zero point 0.6 for kinetic, zero point 0.7 for static. Notice how the static friction is normally larger than kinetic friction. So mu sub k is less than or equal to mu sub static, but usually mu sub k is less than mu sub s. Okay, that's the big principle. Now, to give you an idea of how this is relevant, for instance, to the driving in the snow and ice, I want to go ahead and give you an idea of what goes on with that. So, what I'm going to do is draw a curve like this, and you imagine that this is a road. This is a car, and you can see through the car and see the tires. So, see the little tires? They're all pointed straight forward, and that's because the car is driving forward. Okay. Now, as you get more to the turn, maybe that's the car when it just enters the turn, so it's still going straight. But when you get into the turn, then you're going to have to actually curve a little bit. So then maybe the tires do just a little bit of a curve in the front and they're straight like that. That's normally how you go about turning is you turn your wheel just a little bit to the right to make a turn to the right. And of course, then the direction is this way. But what can happen, especially given that most cars have their engine in the front. There are cars that have the engine in the middle and there's cars that have their engine in the back, but generally speaking most cars and trucks have their engine in the front and the engine's almost always the heaviest part of the vehicle. Yeah, obviously if you're talking about Mack trucks that's a little different because the engine's probably the heaviest part of the truck, but once you add the trailers then the trailers are way heavier and stuff like that. Okay. But the main thing is because the engine is in the front and the engine's the heaviest part, that means the normal force, which y'all can't necessarily understand this yet because we haven't had torque, but the normal force on the front tires is generally larger than the normal force on the rear tires. So the front tires are more likely to have a higher friction force than the rear tires. And inevitably, what happens when you go driving like this is your back end slides out a little bit because of the slipperiness of the road. So if you imagine the car skidding out a little bit, then what you see is your wheel was turned a little bit because you were trying to make that right turn, but now all of a sudden you are going this way and your wheels are turned. Let me use a blue arrow. Your wheels are turned this way. No, anytime you're actually moving in a direction that's not parallel to the pointed direction of your tires, then your tires are skidding. There's not, that's just the nature and definition of a tire skidding is that its ability to roll is this way, but you're traveling that way. So that can't work. So when this happens, what's gone on is the car has begun to slide out to the outside of the curve. And what the weatherman tries to tell you is to turn into the skid. What he means by that, or turn into the slide, what he means by that is if you were driving that car and you were trying to go around a right hand curve, you were turning your steering wheel to the right and everything was going well. And then all of a sudden you felt your back end slide out like this. When you feel your back end slide out like this, what your weatherman wants you to do is turn your wheel that way. So my back end sliding that way, I'm turning my steering wheel that way. The reason why isn't so obvious, but remember if your tires are lined up with the way you're going, then the very bottom of the tire is technically, just the very bottom now, is technically in static friction with the road. It's not easy to see it. It seems a little confusing, but if you think about the alternative, whenever your tire is moving with respect to the road, that's called spinning out. Like you sometimes hold down your brake and push down your gas pedal really hard, and if your car has enough engine, it will sit there and spin out. That's what spinning out is when the tire moves relative to the road. All the other times when you're just driving, your tires are in static friction mode. So that's what you want because static friction we know is greater than kinetic friction. So when you're in this position, notice the wheels are turned pointing in the blue direction of the two blue arrows that are pointing towards the middle of the curve. That's the way your front tires are turned. The red arrow sticking out of the front of the car, that's the way you're going. There's no way your tires can regain static friction at that point. But if you do turn your wheels to the left, then what happens is I'm going to try to imagine blowing this up by just putting it up. Well, actually, I won't even imagine blowing it up. I'm just going to move the car a little bit further forward and assume this is the same thing. And I'm trying not to make a unrealistic angle because tires on cars can't turn but for so far. They don't turn like a whole 60 degrees or anything. But if you did what the weatherman advised you, then you could, in principle, turn your wheels to the left because that's where your back end was skidding out. Now, in this case, your car is now going this way, and your tires are aligned this way as well. If you've done that, then what happens is your tire has the ability to regain static friction. And even though your rear tires can't do a darn thing because they're going to be in kinetic friction as soon as they start skidding, but generally cars don't have the ability to move their rear wheels. There are some cars that are made to allow their rear wheels to turn too, but we're not talking about those cars. So when this happens and your back end starts to swing out to the left, you're supposed to turn your wheel to the left. And the reason why is you're wanting to try to get your wheels to stay parallel to the direction you're going, and that regains static friction. Once static friction is regained, then you have a lot more force, and you can slowly wait for the back end of your tire of your car to be pushed parallel to the front end tires, and everything will be good. So that's one of the main things conceptually why it's important to understand that the static coefficient of friction is generally larger than the kinetic coefficient of friction, and therefore the static friction force is generally larger than the kinetic friction force. And this is also the exact same advice that in the movie Cars, I think it might have been Cars 2. That was the one where they found the old racing guy. No, that might have been the first one, where he told him you had to turn right to go left or something like that. That's the same thing, only he wasn't dealing with snow. He was dealing with gravel or sand or dirt or something like that on the road. He was really dealing with gravel. But the main thing is when you're in that same situation, even if it's not snow, if it's gravel and you start to skid, the same things apply. If you feel your back end shoot off to the right, then you turn your steering wheel to the right. If you feel your back end turn to the left, you turn your steering wheel to the left. All of that's in an attempt to regain static friction. Now, notice that because your tires in your front only turn a certain amount, if it goes too far where you can't turn to get it lined up, then it's just too late. Your things are going to happen. Hopefully, it's not a wreck, but it's definitely going to be you out of control for a little bit. So you've got to pay close attention. You need to be driving fairly slow so that you can react quick enough. But if you're driving too fast, then yeah, you're not even going to be able to react in time. So when you're driving, as you go around a curve, if you feel your back end start to slip to the left, turn to the left. If you feel your back end start to slip to the right, turn to the right. Turn to the left, turn to the right, turn to the left, like that. Okay? All right, with that in mind, let's look at. I've read off some of the coefficients of static friction from Table 5.1. When you're doing homeworks, they're expecting you to use this table if you have to look up anything. It has Teflon on Teflon and air, Teflon on steel and air, rubber on dry concrete, rubber on wet concrete. All that stuff is super. Concrete, remember, that's different than asphalt. Asphalt's that black stuff, and the concrete's that white looking stuff. And normally the concrete has those little expansion brakes. So as you're riding, it's bump, 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 blump, blump, like you're doing on a bridge, whereas asphalt's normally just completely smooth, except for every now and then there'll be something. Now, with that in mind, let's look at example 5.1. So I'm going to go with example 5.1 and I'll read it to you. I'm just not taking the time to write all of that down. So example 5.1 says a 10 kilogram box, and I'll write this in a second. A 10 kilogram box rests on a horizontal floor. The coefficient of static friction, mu sub s, is 0.40, and the coefficient of kinetic friction, mu sub k, is 0.30. Determine the friction force acting on the box if a horizontal external applied force Fa is exerted on it of magnitude, and then it gives you a bunch of magnitudes. So first off, what we have is M equals 10.0 kilograms. Mu static is the coefficient of static friction, and that's 0.40. And mu kinetic is 0.30. And what they're wanting to know in each case is determine the force of friction. So they want to know F equals question mark. And for starters, they're going to say the applied force, Fa, is equal to zero point 0.0 newtons. Okay. Well, that means you have your, object sitting right here and you're not pushing it to try to make it move. So the friction doesn't have to respond at all. In fact, if the friction responded without you applying a force to it, you would be claiming that some kind of magic, like a ghost is in the house or something, because all of a sudden you'd see this little calculator move to the left or to the right. So this implies that the friction force F, which is a static friction force, either way, it doesn't matter. It's just 0 newtons. Okay, so that's one answer. Now for part B, they want you to assume that the applied force Fa, well, I could have wrote that worse. I just can't imagine how. But the applied force F sub A in that case is 10 newtons. Now, I should point out that the kinetic friction is actually equal to mu k times the normal force. And since we said this box sits on a horizontal floor and we didn't say any extra forces are being put on it, then we learned from chapter 4 that the normal force is just equal to the weight. So this is equal to mu k times m times g. So the kinetic friction in this case would be 0.3 times 10 times 9.8, and that gives me a kinetic friction force of 29.4 newtons. Similarly, the static friction force is less than or equal to mu static times m times g, which in this case is going to be 0.4 times 10 times 9.8, and in that case we get 39.2. Okay, now we did have 2 sig figs with the mu, so we only have 2 sig figs. So that means this kinetic friction is 29 newtons roughly, and the static friction is 39 newtons roughly. So when I apply a force of 10 newtons, notice that's smaller than the static force, right? The static friction force can go all the way up to 39.2 newtons, which again, the 0.2 is not supposed to count, but it can go all the way up to at least 39 newtons. This is less than that. So the applied force, according to that graph I just showed you, F applied, F friction, that's what I was trying to say. I don't know why I put an A on there. The friction force in this case is going to be the static friction force, and in fact, it's only going to be 10 newtons. because it didn't need to be the whole 39. It just had to cancel out that force that was trying to make it move, and that force was smaller than the 39, so we're good. Now for part C, the force is 20 newtons. So the applied force is 20 newtons. That's still less than the static friction force maximum. So static friction is sufficient to keep it from moving. So the force will be a static friction force, and the force will be 20 newtons. Again, that's just what I was showing you with this, because whatever force you apply is exactly equal to the friction force, exactly equal to the friction force, exactly equal to the friction force up till you get to here. And then that's our 39.2 is that peak value there. And this is our 29.4, whatever that number was. Yeah, 29.4. Okay. So that's what happens with the 20 Newton force. Now I'm going to see part D. The applied force is 38 newtons. Anybody tell me what the friction force will be? For starters, is it static friction or is it kinetic friction? Anyone? I'm going to make sure my chat box is on so I can see if anybody tries to type the answer. I do not see anybody trying to type the answer. So notice the 38 newtons is still smaller than the static force. And as long as you're smaller than the static force is just going to come up and match it. So in this case, it will be static and it will be 38 newtons. Now we jump to E. And for part E, the applied force is actually going to be 40 newtons. So notice at 40 newtons, that force is greater than the static force max. Okay? Because the static force max has got to be basically 39 newtons, period. If you wanted to add extra sig fig, it'd be 39.2, but roughly around 39 newtons is all the static force can come up with. So in this case, it exceeded the static force. That means it's definitely going to move. We don't have any choice about that, but that's going to cause it to go into a kinetic friction. And then the kinetic friction always acts with exactly the same magnitude, as you can see here by the horizontal line after you got past the max. And that amount is mu k times the normal force. So this friction force is in fact 29 newtons. So those are the answers for that. And in fact, we can go ahead and since Newton's second law says the summation of the forces is equal to mass times acceleration, in this case, we would get 40 newtons in the positive direction plus a negative 29 newtons, and it's negative because it's pointing in the negative direction, is equal to 10.0 kilograms times the acceleration. Well, 40 minus 29 is 11 newtons, and that's equal to 10.0 kilograms times A. So A is going to be approximately 1.1 meters per second per second. So that's what would happen if we applied a force of 40 newtons to this particular 10 kilogram box with these coefficients of friction. Anybody have any questions on that?
Yeah, Professor, I had a question. Where did you get that 38 and the 40 Newton from? Was it from the textbook, the example from the textbook, or?
Yes, so I'm going from the example in 5.1, and that gave us the mu s was zero point 0.4 and the mu k was zero point 0.3. Then I'm just using the formulas that I just finished giving you guys for static friction and kinetic friction. So remember, static friction is less than or equal to mu s times the normal force. Kinetic friction is just always mu k times the normal force. Okay.
Oh, okay.
that less than or equal to is just showing that it's going to be as big a force as it needs to be up to some maximum value, at which case it can't go any further. And that's the mu s times the normal force.
All right, got you.
And since this was perfectly horizontal, we knew, and no other forces were acting on it, that we knew that the normal force would just be mg.
Okay, thanks.
No problem. The next example is really a conceptual one. Uh, so I think I'm going to fit it here because it's more about the explanation that matters. This is example 5.2, and it says, box against a wall. You can hold a box against a rough wall and prevent it from slipping down by pressing hard horizontally. How does the application of a horizontal force keep an object from moving vertically? That seems counterintuitive, right? I'm pushing to the left, but somehow that holds something up. Well, that's because there's a linkage between the horizontal force that I apply to the object that's up against the wall. Remember, the normal force doesn't have to point up or down, it just has to point perpendicular to the surface. So, if, for instance, I took this Rubik's Cube and this is a wall, right? It's if I just laid it here, it's going to fall every time, right? But if I push it hard enough this way, then what's happening is Newton's second law, the summation of forces in the x direction equals mass times acceleration in the x direction. If I'm actually pushing it against the wall that's sturdy enough, then the wall is not going to allow it to move. And since the x coordinate is not changing and it's still not changing, that means the acceleration in the x direction is zero. That means whatever force I applied here minus the normal force must add to give me zero. That means whatever force I apply here is equal in magnitude to the normal force. So if I push that hard enough, I can get the normal force bigger and bigger and bigger until I actually can take the mu static and multiply it by the normal force. If I get that that quantity is equal to the weight of this object or higher, then it will stay still against the wall. All I had to do was make sure that the coefficient of friction, I can't change that by pushing harder or softer, but I can change the normal force. So if I pushed it at one force and it still slid down, I'd know, oh, the normal force isn't large enough. So I'd push it a little harder still. And then if it didn't move, I'd say, okay, that's probably good enough. And that all depends on what the mu is for that particular surface of the Rubik's Cube versus whatever surface of the wall is there. Anybody have any questions on that? Okay. So if mu static times the normal force is greater than or equal to mg, then F mg, then F minus mg is equal to zero implies object does not fall. So that was really what had to happen. Uh, what I was doing here was applying a force F applied, and from that I was getting a normal force Fn, where F applied equals F normal. So as long as I get it such that the mu sub s times the normal force is greater than or equal to mg, then the object's not going to slide down the wall. Anybody have any questions on that? All right, looks like no one typed any or asked any, so I'm going to go on to example 5.3. This one says pulling against friction. A 10 kilogram box is being pulled along a horizontal surface by a force FP equals to 40 newtons applied at a 30.0 degree angle above horizontal. This is like example 411. We did work that before, except that there is now friction and we assume a coefficient of kinetic friction equal to 0.30. So what I have is the mass is equal to 10.0 kilograms. I have FP is equal to 40.0 newtons, and I have theta equals 30.0 degrees. I also have mu kinetic is the one they gave me, so mu kinetic is 0.30. And now what we want to know is what is the acceleration A equals question mark. So what we have is really a box whose mass is 10.0 kilograms, and we have acting on it a force FP that makes an angle of theta equal 30.0 degrees with the horizontal, and it has the potential to slide left and right. So what I'm going to do now is draw the free body diagram. So there's my X, there's my Y. As I told you, until we learn about torque, we're going to treat all things as if they're point particles. And the forces acting on this are, of course, this force, which has not been rendered into component form parallel to the X and Y axes. That's just FP, and this is 30.0 degrees. Now, in addition to that, I have a normal force which acts upward, so I'm going to give that the green arrow. That's F normal. And then pointing down, I have the object's weight, and weight is equal to M times G. So in this case, it turns out to be 98.0 newtons. And then we also have a friction force, which is also acting in the negative direction. Now, it's kinetic friction. So the kinetic friction has a fixed formula. It's just mu K times the normal force. Okay. Now I need to break FP up into components. So it has an X component that is positive, and it has a Y component that's positive. So this is FP sub Y, and this is FP sub X. And until you get super comfortable with using the trig function, just go ahead and write sine and cosine for each of them and then solve. So I'm going to say sine of theta is some old horse or so, sine equals opposite over hypotenuse. That's FPY over the hypotenuse, which was the 40.0 newtons. That means FP sub Y should equal 40 times the sine of 30, and I think that turns out to be 20. And cosine theta is equal to adjacent over hypotenuse. The adjacent is FP sub X, and the hypotenuse is 40.0 newtons. So FP sub X is equal to, I'm going to take 40 times cosine 30. I do have it in degree mode. So that's 34.64 newtons like that. So now I can go ahead and write the summation of the forces in the y direction equals mass times acceleration in the y direction. Now, as I'm pulling up on this box is still sliding perfectly horizontal, and that means the y coordinate is 0. I've got it drawn right at the coordinate origin, so the y is 0. If I wait a tenth of a second, it's still 0. If I wait another tenth of a second, it's still 0. So the acceleration in the y direction is equal to 0. I'll go ahead and write that. Now I take all my forces in the y direction. They are the normal force, which points up, so that's a positive, as you can tell by the green arrow. Then I have the weight, which points in the negative direction. So it's technically being added, but again, I don't want to write plus a negative, so I'm just going to write it minus 98.0 newtons. And then the FPY is also in the positive direction, so that's going to be 20.0 newtons. And then all that adds up to 10.0 kilograms times 0, which means that whole side is 0. And this gives me that the normal force is actually equal to 78.0 newtons. Everybody sees how I got the normal force? Any questions on that? Now I'm going to do the summation of the forces in the x direction is equal to mass times acceleration in the x direction. Now, we're actually intending to pull this box. We're pulling up with a little angle that's actually good, managed to decrease our normal force a little bit and made it a little bit easier because now the friction force is going to be less. But we now want to calculate the acceleration. So the forces acting in the positive x direction is just FPX, and FPX is 34.64 newtons. And then the friction force is going to be mu kinetic, and notice it's in the negative direction. So I'm taking plus a negative quantity, but I just write that as minus. That's going to be 0.30 times the normal force, which is 78.0 newtons. And that's the only two forces acting in the x direction, and that's got to be equal to 10.0 kilograms times A. If I take zero point 0.3 times 78, I get 23.4, so this becomes 34.64 newtons minus 23.4 newtons is equal to 10.0 kilograms times A. 34.64 minus the 23.4 gives me 11.24 newtons is equal to 10.0 kilograms times A. So finally, we get A is equal to 11.24 divided by 10. That's 1.124 meters per second every second. That's the acceleration. And obviously, that's an extra sig fig, an extra digit that's not a sig fig, I should say. Anybody have any questions on that? Technically, actually, there's two. Uh, this 23.4 should only have two sig figs, so that one makes that not good. And then when I add the two, that makes that not good. So neither the 2 nor the 4 is a significant figure, so we'd have to call that 1.1 meter per second every second. Any questions on that one? All right. So that's supposed to be a pretty straightforward type of example. Uh, let's look at example. Well, actually, conceptual example 5.4 is a good one. So I'm going to talk about that a little bit. Let's go back to example 5.4. It says, your little sister wants a ride on her sled. If you are on flat snow, will you exert less force if you push her or pull her? assume the same angle theta in each case. So what they mean by that is if this is your little sister on her sled, okay, and you are pulling her via a rope, say, this is an angle theta, and you're applying a force F, okay, that's you pulling. If you're pushing the sister, then what happens is you are pushing down now with an angle theta, and this is the force F again, but it still has the same angle theta. Now, can anybody tell me which one of these scenarios, the pushing your sister or the pulling the sister, which one's going to result in a larger normal force? Anybody guess that one? All right, let me draw the free body diagrams. So there's our X, there's our Y. What we have in this case is a force that's not broken down into components yet. It's basically a force that's on a diagonal at an angle theta. So what that's going to have is a positive y component and a positive x component. And then we're going to also have a normal force Fn, and we're going to also have a weight W, and we're also going to have a friction force F. We're actually pulling her, so this is kinetic friction. That's equal to mu kinetic times the normal force. Now, on the pushing diagram, it's more or less the same thing, but there's a little difference that hopefully you all have already figured out. So, in this case, we have the force acting downward like this. Oop, why did this just disappear? Hold on a second. Did y'all just lose my screen too? I lost it on my side.
Yeah.
Okay, cool. Good. Making sure something bigger hadn't happened. All right, so there's that force and there's that angle theta again. This time we have a component of the force in the y direction is negative, but the component of the force in the x direction is positive. So we have the same pulling force, the horizontal one, but the uh, pulling force component in the y direction is opposite in the two scenarios. We still have, of course, the normal force, F normal, and we still have, of course, a friction force, which is F kinetic equals mu kinetic times the normal force, and we still have the weight W acting downward. So if I take the summation of the forces in the y direction equals mass times acceleration in the y direction, and that's equal to zero, what we get is Fn, that's in the positive direction, minus Fn sine theta minus W is equal to zero. So you can see that even if we try to solve for Fn, we get Fn times 1 minus sine theta is equal to W, so Fn is equal to W over 1 minus sine theta. And of course, sine theta can only get as big as 1, but that would really be a problem. The main thing is you see that the normal force is definitely less than the weight. If I do it over on this one, the summation forces in the y direction equals mass times acceleration in the y direction. In this case, I've got the normal force pointing up, but I also have plus Fn sine theta pointing up, and then I have minus W, and all that's equal to 0. So I get Fn times 1 plus sine theta is equal to W, or I get that the normal force is equal to W over 1 plus sine theta. So now you see that since I'm subtracting sine theta on the right hand side, that means the denominator here is smaller than 1. Since that's less than 1, that means the normal force is going to be bigger than the weight. Over here, I'm going to take 1 plus the sine of theta, and theta doesn't make any sense unless it's between 0 and 90, so it's never even going to get to 1. But what you see is I'm dividing by a number that is greater than 1. Therefore, Fn is actually less than the weight here. And since the friction force is proportional to the normal force, we see that in the case of pulling, we've actually decreased the normal force. Therefore, we decrease the friction. Therefore, we can pull her more easily and more quickly than we can push her. Does that make sense to everyone? Anybody have any questions on that? All right. So,
Would that change? Oh, sorry, I had a
go ahead,
question.
Isaiah. What's that? I can barely hear you, bud.
Would that would that change if like I had like weights on my feet?
Yeah. So if you had stuff on your feet or whatever, that could increase the weight. But if you compare apples to apples, what you're supposed to do is assume the sister is on the sled in exactly the same situation, same weight of the sister, same weight of the sled. The only difference is the in one case the angle is downward that we're pushing her, in the other case the angle is upward that we're pulling her, but everything else is supposed to be equal for this particular problem. So in
Okay,
that scenario, that's why I have to reach the conclusion that pulling her is more efficient than pushing her. But yeah, if you add other things, if you add more weight, that's going to be a problem. You could also allow her to hang her feet down. If she was wearing like ice skates, you could allow her to hang her feet down, and her pushing down would actually make the normal force less as well. So that could help too. Anything else? Did that answer your question, Isaiah?
yes.
Okay.
Thank you.
All right, so that's the typical scenarios with friction. There's a lot of different problems we can solve. We can do Atwood machines and all that good stuff. And I'm going to work some more of those, but I want to go ahead and get you into being able to solve the rotational motion problems, which obviously, since we will have a meeting next time because you guys meet face to face at night. So next time we're going to be solving more problems, but I want to get you ready by introducing you to circular motion. So with that in mind, let's take a break from this for a second, and I'll do more examples next meeting. But right now, I want to go ahead and give you an idea of something interesting. So it turns out you can write a vector valued function. Notice what I just said. I said vector valued function. That means you put in, function means you put something in like function of x, you'd put in the x. If it's a function of x, y, and z, you'd put in the x, the y, and the z, and out comes a value. You're just used to that as a function where you put in one number or two numbers or three numbers and out pops a number. That's just a function. A vector valued function means you put in a number or multiple numbers or whatever, and out pops a vector. So our position vector, which we can treat as a function of time, is going to be equal to, and I'm making a very special one here that hopefully you'll recognize it. If you don't, that's okay. It just means you haven't thought of this before or you haven't been exposed to this before. But there's two ways I can write it. One, I'm going to write it r cosine 2 pi over the period t times time, lowercase t. So notice the big T is the period of the orbit. That's something we'll hash out in a second. I hat plus r sine 2 pi over t j hat. That's one way we can write it, but it's not the most efficient. It's really good for the table I'm getting ready to make, but the better value is this r cosine omega t I hat plus r sine omega t j hat. So omega is just the same thing as 2 pi over t, which also happens to be 2 pi times the frequency. That's frequency, something y'all haven't heard of yet, but you might have heard of it just, for instance, by having a radio. Does anybody know why radio is relevant? Anybody want to tell me what does frequency have to do with radio?
Radio's transmit frequencies.
Exactly. Your speaker doesn't work too good. I can just barely make you out, but that sounds like you said the right thing, Isaiah. Yeah, my daughter once asked me, "Daddy, do those numbers or do they mean something, or is that just something the car company put on the stereo?" She was like 6 or 7 or something like that, and I said, "Yeah, they mean something." And then she was sorry she ever asked me because then I went to explain to her that when you're in the AM, that's amplitude modulation, and 850 AM means 850 kilohertz. That's the frequency of the radiation put out by the antenna that 850 the buzz puts out. Whereas the FM means frequency modulated, and for instance, 93.7 Bob FM is 93.7 megahertz. That's their frequency. So that's the relevance of these two. Now, this might not seem all that relevant, but it teaches us a lot of things and it gets you ready for a lot of things. One of the things you're learning in 241, 242, and if you take a third semester, 243, is vector calculus. Okay, so that means applying calculus to vectors. So, for instance, since I'm using R, that's just like the position vector. Some books will use X. I don't like X because Y is X more important than Y or Z. So I like to use just plain R for the position vector. But when you do that, that means the velocity vector, V of t, is dr over dt. And the acceleration vector, A of t, is dv over dt. So extra credit for you folks, and this is an extra credit that you could skip, but I highly, highly, highly advise you not to. In fact, I would put this as a higher priority than starting your homework for Chapter 5, is to do this extra credit. The extra credit is I want you to make a table of time in seconds, X in meters, and Y in meters. And the times you're going to choose are 0, t over 8, and then 3. Well, actually, let's do t over 4. Somebody just came in. I got to let them in. So now I'm going to say t over 4 is the next line. And then 3t over 8 is the next line. And then t over 2. And then 5t over 8. And then 3t over 4. And then 7t over 8. And then t. So your job is to figure out, notice this part right here is x in meters, and this part right here is y in meters. So your job is to fill this out. For instance, when I plug in 0, cosine of 0 is 1. So I get, in fact, r for the x value. When I plug in t equals 0 for the y, I get sine of 0, and the sine of 0 is 0. So that's going to be 0 there. Similarly, if I put in t over 8, then that basically becomes the cosine of pi over 4. And of course, the cosine of pi over 4 is 45 degrees. So in this case, you get about 0.707 R and 0.707 R there. And then when you get to 4, t over 4, that's going to give you a 0 here and an R here. So your job is to finish out this table. I gave you the first 3 lines, but you should be able to do that. Then I want you to calculate this, and I want you to calculate this. All these things with the red lines under it are what you're supposed to do. Now you're also supposed to calculate the magnitude of V of t and the magnitude of A of t. Okay? So I want to remind you the magnitude, when you have a vector that's in IJK notation, then all you have to do is square the thing that's in front of the I hat and square the thing that's in front of the J hat, add them together and take the square root. That'll be the magnitude. When you do that, you will find using a certain trig identity that the t will cancel out. You won't have any t dependence on the magnitude of the velocity or on the magnitude of the acceleration. So your job for extra credit is to one, fill out this table first. That's the very first thing you're supposed to do. The second thing is you're going to calculate v of t by taking the derivative of this. Notice the derivative when we're looking at this, the capital R, the 2, the pi, the capital T, they're all constants. So when you're taking the derivative, you're just taking the derivative with respect to time, and everything else is a constant. But you got to follow the chain rule, and I'd highly recommend you use the version with omega as opposed to the version with 2 pi over t. But you're going to take the derivative of R, and that'll give you V of t. Then you're going to find the magnitude of V of t. Then you're going to take the derivative of V of t. That'll give you the A of t. And then you're going to find the magnitude of that. And then when all that's done, you can actually take and try to make this as big as possible. Because if you make it too small, the diagram will get really, really messy. You're going to have a y-axis and an x-axis. What you'll see is there's an r vector right here that goes out to a distance r, and this is at t equals 0. Then there's another one at t equals t over 8. And then there's another one at t equals t over 4, and so on and so forth. Oops. All of these are going to have exactly the same length as each other, but you'll end up having 8 arrows. All of those arrows are pointing to the position of an object that's traveling in a circle in a counterclockwise direction over time. Then you can plot the velocity, which you're going to find turns out to be perpendicular to that, and perpendicular to that, and perpendicular to that, and perpendicular to that, like this. And then you can plot the acceleration, which lo and behold is actually going to point in the opposite direction of R. So the green vectors are A of t, and the red vectors are V of t. Okay. Now, if you do all that, what you'll discover is the magnitude of A is actually equal to omega squared times R. And when you calculate the V magnitude, you're going to find that that magnitude is omega times R. So that tells you, for instance, that omega would equal V over R, and you can plug that in here, and you'll get V squared over R squared times R, which equals V squared over R. And that is what we call our centripetal acceleration. Notice what I said there. Centripetal acceleration. Centripetal means center seeking. So, in order for something to go in a circle, it can't just go, I mean, it could go at a constant speed, but it can't go at a constant velocity because velocity is a vector quantity, has a magnitude and a direction. So, even if you kept the magnitude constant, if you went in a circle, you were changing the direction. So you were accelerating. And it turns out the bare minimum acceleration you can have to maintain a circle is the centripetal acceleration given by v squared over r, which is also given by omega squared r. Either one of those would work, but we normally use v squared over r. So by you going through this extra credit process, you're going to come up with a graph of all these velocities and all these r's and all these accelerations. You're going to find the magnitude of the velocity is omega times r. You're going to find the magnitude of the acceleration is omega squared r. And then you're going to find that that, of course, is equal to v squared over r. And you will then have done basically what your textbook does, which is it created a derivation of the centripetal acceleration. So that's what you need to be able to do in order to solve centripetal acceleration problems. So we're going to examine, for instance, a car going around a curve and figure out exactly what kind of friction force you'd have to have between the tire and the road so that the car doesn't skid out of it as a result of how fast you're going around the curve. Not only that, we'll calculate at what angle you could bank a curve so that you don't need any friction to make the turn. Of course, the downside would be if you really didn't have any friction and you went too slow around that curve, then you would drift down into the center, which, you know, if you've ever rode off of an exit ramp, you know that in the center of the loop of the exit ramp is normally like a pond or, you know, some kind of cliff or something. So that would be suboptimal at best as well. Anybody have any questions on what you're going to do with that stuff that I just gave you? I've already typed it up. It'll be in this week's module. I just got to move it there because I put it in the face-to-face class module already. I just haven't put it in your module. So I'll put it in your module for this week, and you'll see it's like extra credit 6 or something like that. Anybody have any questions on that? Okay. Well, there's one last thing that I wanted to show you so that you'd have a complete picture of chapter 5, and then I'll do more examples next time. The other thing is air resistance. And it turns out the drag force, F drag, are air resistance. Well, the drag force is either proportional to V or it's proportional to V squared. Okay. It turns out the V squared is more important when you're going really, really fast, or if you're going through a really, really dense liquid, that's more problematic. But a good fraction of the time, you can just say the air resistance is directly proportional to the velocity. But one of the things that is, makes it equal as opposed to just proportional is the cross sectional area. So, for instance, if I dove head first towards the ground from an aircraft, the air resistance would be proportional to V or V squared, but it would also be proportional to the area that my body covers. So if you imagine the sun shining straight down, which it doesn't do normally, right? But we're going to pretend like the sun is shining straight down, then I would get a shadow. A shadow of me would look something like this, where these are my shoulders and this is the front of my head and this is the back of my head. That total area there is what the drag force is proportional to. So we say the drag force is some constant times the area times the velocity, or the velocity squared. I'm going to go with the velocity right now. This has to do with the air that we're going through. So that's some constant that has to do with the viscosity of the liquid or the fluid that we're going through. For instance, if we fell through water, that would be one thing, but to fall through syrup would be something different. So that C takes into account whether it's syrup or water or rubbing alcohol or whatever, and the A is my cross sectional area. Now, if I if I fell out of an aircraft and I didn't have a parachute and I wanted to try my best to survive, then what I would do is spread my body out like one of those flying suits that you see skydivers do, because then my area is really a maximum. And that would make the drag force a lot higher. And what happens when an object is falling is you have a force W equals mg pulling you down, but then you have a force slowing you down, FD, which is equal to C times A times V. Once the V gets to some critical value, then the C times A times V is equal to mg. You've reached now terminal velocity. Okay? Terminal velocity occurs when the weight, which is the force pulling you down, is equal in magnitude to the drag force that's slowing you down. Now, it's not always going to look like C times A times V. The important thing is the drag force is going to be some constant times V. And your job might be just say F drag is equal to B times V. Then you say terminal velocity implies BV equals mg. So V terminal is equal to mg over B. All right. I'll do more with that next time. I'll actually derive the equation of motion. So I'll get the x as a function of time for it. But right now, I just wanted to get you guys started where you can start doing your homework and, of course, start doing your extra credit assignment. But now you can do your homework as well. That's it. You guys are done. You're free to go. If you haven't sent me your first and last name in the chat yet, make sure you do so now. I'll wait here for the last person to leave. Other than that, you're free to go. And remember, we have a test next time or sometime this week for you guys. We are meeting next time for class.
Thanks. Have a great night.
You too. Thanks, Michelle.
Prof, I had a
But
quick question.
oh, sorry.
Oh, my
Yes.
bad.
Go ahead.
I don't know who's going first. for the test on Wednesday,
Uh-huh.
can I like just come in or like do I have to like formally like do
No,
anything
you
to
just
be
show
there?
up and introduce yourself to me. I'll be either in JC 21 or JC 22. You'll see me somewhere walking down that hall. I'll be in one of those two classrooms. And you don't have to take it Wednesday. That's just one of the proctoring times I have available to you. I'll also have an online proctoring time as well sometime next week or maybe even Monday after this week. So all this week are days that you're allowed to do it at the testing center, including Monday of next week. I've already submitted that, so you guys are free to do that. But I'm also going to have at least one time, maybe two times, that I can proctor it myself over the internet. So just, if you want to do it over the internet, you need to let me know. But if you're just going to show up to class, you can just show up. If you have your own laptop that you can bring with you, that'd be great as long as it can run on the Wi-Fi on campus and as long as it can run Canvas and the tests in Canvas. But other than that, we have computers that you can use.
Okay, so Monday it would be like it would be on the computer though, or is it on paper? I'm kind of
Yeah, so what I've done this time is I put it on computer, but it's some of the things are multiple choice, so you'll just type in the multiple choice for it, but you're going to turn in your work to all of them, and I'm not necessarily going to give you credit if you get the right answer, but don't show me work. So you got to remember that, but it will be on the computer this time. If it doesn't work out, next time I'll probably just do everything on paper, but right now I'm still trying to do as much as possible without using paper.
so it's okay to turn in like some of the scrap work that we did
Yeah,
in the
and you want to
testing.
be as neat as possible because that's really what's going to be the difference between you getting a zero for a wrong answer and you getting, 8 out of 10 points for a wrong answer.
Okay, and then all right, so I could call them up because I have a class typically right after in the afternoon on Monday. So if I could test at that testing center, is that okay?
Yeah, absolutely. As long as they can grant you the appointment that you're trying to do, and the earlier you make that, the better off you'll be. But I've already submitted the application, so you guys can do any time between today and a week from today.
Okay, so as long as we give you like the heads up that we scheduled something, we won't get like a zero or anything like that.
Exactly. And if something
Okay,
comes up where you end up not being able to do it by Monday, just let me know. Sometimes we have some problems where you just can't fit it in, and I can give you an extra day. It's not that big a deal. Just hopefully everybody will be done by Monday.
thank you so much, Professor. I do appreciate it.
No problem. Have a good one, Isaiah.
You too. Bye bye.
Somebody else was trying to ask something a second ago. Anybody? Was that Ben?
Yeah, it was me. I just had a similar question to
Isaiah?
Isaiah. So for the test, you said that we can go to the testing center, right?
Yeah,
To do
you
it?
have to, they require appointments, I'm sure, so you want to make sure you find out that and what you need to bring. Normally, you'll need a photo ID and that sort of thing. The equation sheet is built into the test, so you'll see it there. If you want your own hard copy, it has to be exactly the same as the one I use, and they're going to take a picture of it and send it to me. If it's different, then you end up being counted as cheating, so don't do that. But the equation sheet and the table from the inside the book, everything that you see on your practice test that down at the bottom will be available for you on the actual test.
Okay, and I had another question. So when is the test? Do we have like a week from Wednesday, you said, or we have to get
You
it done by
have
Monday?
today was the first day you could take it. You have Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, Monday, and that's it. Uh, the testing center, I don't know of any testing centers that are open on Sunday, but there are some testing centers that are open on Saturdays, but you got to make sure you make an appointment with them and that you can meet their requirements. But you can do it any of those days, or you can also attend during my classes on Wednesday, which I mentioned at the beginning of this, or you can wait for my email. I'm going to tell people when I can do a proctoring over the internet via Zoom. So if you can't go to a separate campus, you can actually do it while I watch you over Zoom.
Okay, thank you.
No problem. Anybody else have any questions? Everything okay, Riley?
How you doing today, Professor?
All right. I can barely hear you though. Your speaker's really quiet.
Is that any better?
Yeah, I can hear you a little better now.
I think I just had to speak up.
Gotcha.
So, you mentioned a face-to-face class on Wednesday.
It's there's actually two times that you could do that. In principle, we might even be able to do a third time, but we'll see.
Is is that just to give the option for like the test, taking it face-to-face and being proctored?
Yeah, if if you have some problems or whatever, and you don't want to necessarily try to make an appointment at the testing center, but you'd like to take the test and get it over with, then you can come Wednesday and have it taken. Also, if you don't want to do that, you can have me proctor it on the at least one other day where I'll offer it via Zoom, in which case I could proctor you via Zoom.
Okay. I planned on I'm actually in the process of right now making an appointment at the Portsmouth Testing Center for Monday.
Okay, that should be cool.
And then if you send out an email with like, hey, these are Zoom proctor
Yeah,
times, like
I'll give you
that just
times.
works.
I haven't worked out exactly what times that I'll be doing the Zoom one, and I'm trying to see if I can fit in two instead of just one.
Mhm. Yeah, if that time works out, I'll probably just cancel that and hop onto that.
Yeah,
But
that'd be a
if
good idea.
if we are doing either the testing center proctored or the Zoom proctored, do we need to do the in-face class on Wednesday? Or is
No,
that
no,
still
that's
okay?
just another option for you. You're allowed to do it any day this week or Monday of next week, whichever one works best for your schedule. Each student's test will be a little different, so but you still shouldn't talk to each other about it because you'd give whoever takes the test last, they would get an advantage. But generally speaking, if you take it on Tuesday and someone else takes it on Thursday, there's going to be a slight difference between the Tuesday version and the Thursday version, or even between the Wednesday version in the morning and the Wednesday version in the afternoon. So, but there is enough overlap where you could definitely harm yourself or harm someone else if someone got an advantage of hearing what's on it.
Oh yeah. And I know there's that large pool of questions, 80% from the practice stuff.
Yeah, and I've made it already, and I decided to do 100% from the practice questions. The only difference is some of them I made into non-multiple choice, and some of them I even changed the numbers a little bit. So you just got to pay attention and actually work the problem. The main thing is I've discovered there are a small fraction of students that are able to game the system, and I have to get rid of that because I've got students that I can ask them how to solve a problem and they can't tell me, and they make straight hundreds on their face-to-face tests. So they're literally just memorizing all the answers that come up.
Oh, that's crazy, especially if you need physics
Yeah,
for
and
like
it'll harm you if you become an engineer or someone who does calculations that are important. It could really be a problem for you. So
oh,
that's what I'm just
that,
trying to do is stop that because I know how easy it is to fall into temptation. I don't want people being tempted by an easy test scenario. I'd much rather them figure out how to solve the problems.
oh yeah. So like the practice test after like the the graded ones that we get or the
Hmm.
extra credit technically,
Right.
um those close up after the date. So
The
would you
close up
recommend
on the very last day. So you guys, which are online, so you have Monday until Monday. I close that at 11:59 p.m. on Monday. Not today, but next Monday at 11:59 p.m. The practice test will disappear.
Mhm. Okay.
Okay.
Oh, I was just thinking like since the practice test for chapters 1 and 2 and then 3 and 4 separately are already closed, would you recommend going through like the practice problems for 1 through 4 and all that? I
Yeah,
forgot
so
about the
I
practice.
just posted a new practice test that's for the online test, and I did it because of that, because my
Mhm.
242 students and some of my 241 students already finished their online test too. And even though it covers the same material as the face-to-face test, I went ahead and made another face-to-face practice test that you have to do to get credit. But now that's open until the last day of the face-to-face test.
Okay.
And I
And
sent some
then
announcements about that, so you check your email too.
yeah, I think I definitely looked at that. I've my brain has just been really scattered
Oh
lately.
yeah, yeah, I get you. And I sent two of them, so that didn't make it any better.
And then final question I had, this is more about like
Mhm.
works and all of that. Um, oh wait, never mind. I also,
You figured it out?
sorry. Yeah, I know chapter 3 technically in the grade book isn't due until tomorrow. I've
Yeah,
gone
I
through it.
just changed those dates. I noticed some of your dates I had changed them, but they seemed to not take. So I just gave y'all another chance to do chapters 3 and 4. I moved the due dates on those intentionally to give y'all a little bit more time.
Mhm. Yep. Okay.
All right,
I appreciate it, Professor. I'll go ahead and get that scheduled and look for any emails.
no problem. Sounds good. I appreciate it, and let me know if you need anything.
Awesome. Appreciate it, Professor.
All right, have a good one, Riley.
Thank you, you too.
Bye bye. Okay, that looks like it. Bye, everybody.